Swayam Prabha. Digital India. Educated India.
Tomorrow the 2.1 will be about Navier-Stokes equations of fluid mechanics, okay? Because sometimes people coming from the classical thermal physics and thermodynamics, they are not doing fluid mechanics and vice versa, okay? So it's very important. And again, we are going to have a bridge with everything together. So, phase change. Again, these are the classical four phases, solid, the gas, plasma, and liquid. And we would like to understand what is happening when we are going from one phase to another. Okay? So, first of all, we need to study this kind of phase transition, looking at the equation that we said before. And one point is that we can think to the phases in a way that if they are close in the same system, they are like a simple system separated by walls that are diathermal, movable, so they can move, and osmotic. And so looking at the equilibrium, when you have a diathermal wall, you have the same temperature. When you have a moving wall, you have the same pressure. And we have an osmotic wall, you have the same chemical potential. Okay? This is what is happening in terms of equilibrium of the phases. So, for each phase, we can write the expression that we saw before, so that the entropy multiplied by the T for a given phase, so solid, liquid, gas, equal to VK dP, K, and minus the sum all over the chemical species of the moles of the phase multiplied by D of the differential of the chemical potential. So this is the Gibbs-Duhem equation. And then we can write this for each chemical component and each phase. So if the system has m phases, the equilibrium, the postulate, says that for a monocomponent we are R plus 2, no variables. If we have m phases, we need then m multiplied by R plus 2 variables. Okay? So of course the Gibbs-Duhem is not enough, but what we have is that we have, since the walls are, let's say, diathermal, osmotic, and movable, we can have that we have the equations for the equilibrium. So for each intensive variable, we are going to have the temperature in one phase is equal to the second one, blah, 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 until the m phases, if we have m phases. The same for the chemical potential, only that the chemical potential number of K chemical potential, because we have K species, chemical species. Now, as you know, the number of variables minus the number of equation means the degree of freedom of the system. So since we have mr plus 2, m multiplied by r plus 2 variables, as we said, we have how many equations? Here we have, let's say, m minus 1, because we can do this one, so at the end we have minus 1 multiplied by r plus 2, so, and then we have the other one of the Gibbs-Duhem. So at the end we are landing with this expression. So we know that we have r plus 2 minus m degree of freedom. So if the system has one component, so r is equal 1, and three phases, r1 plus 2 minus 3, there is no degree of freedom. So in this sense, we have that PT, pressure, temperature, and chemical potential, this is not an m, but is a mu, sorry, are unique. So we have only one point. In fact, it's a so-called triple point. Okay? So the temperature must be equal, the pressure must be equal, and the chemical potential must be equal. Okay? So when we have two phases of a monocomponent system, the system cannot be at any arbitrary temperature and pressure, but if we measure the temperature, we are going to have one pressure and vice versa. If we know the pressure, we know the temperature. So in fact, we have one curve. And in this way, we can build, for example, the Clausius-Clapeyron chart, graphs, okay? Another point is that we saw that the free Gibbs energy is in fact related to the potential, chemical potential. So a phase equilibrium curve is decided when the chemical potential is the same. So in fact, what we have is that for a given pressure and temperature, we have the variation of pressure and the variation of temperature are linked to the Gibbs expression. Again, something that you should know. So I'm very fast, but at the end, since we can express the fact that we have the same potential and the same variation of the Gibbs, the free Gibbs energy, we can derivate. I don't have time to do it. This is for my undergraduate students. So what we have at the end is this expression that is saying that the variation of pressure related to the variation of temperature is linked to the latent heat and the difference between the density of the two phases and temperature, and the temperature at which we are, let's say, defining the value of this derivative. Okay, and this is important because we can have, let's say, this expression. We can have kind of, for example, simplification. We can try to plot the solid-liquid boundary, the liquid-vapor boundary, and so on and so on. This is, for example, speaking about phases, solid, gas, vapor, and so on. See that we said that the water has 12 phases. These are, for example, now 11, for example, phases of the water. As you can see, this is happening at very, very high pressure. So, but it's interesting to know that, for example, we may have water up to almost 500 Kelvin. So we have water at 200 Kelvin, 200 centigrades. We have solid water. Of course, we need to go very high with the pressure, but it's possible. Okay, these are states of the water that are very interesting. Okay, but I don't have time now to enter. Again, this is again interesting, and this is the classical Clausius-Clapeyron. I think that everybody of you knows this graph, so I don't want to spend time on that. I have more material, more important material afterwards. The triple point, I think that everybody knows about that. When we have, let's say, solid, liquid, and vapor together, and we have 1 point because we don't have degree of freedom, as we said. And the phase transition are, let's say, we are considering somehow stable in the condition that where they are occurring. I don't have time. This is something that I'm giving to you later, so it's not important. And then we have this kind of very known 3D charts or 2D charts for the pressure and volume and so on and so on. I think that, okay, everybody knows about that, so I think that everybody knows. Okay. Sorry, I was fast. I will give you the PDF, but this is only something that you should know. Okay, I'm giving for granted. Okay. If you don't know, please look at the slides. Okay. More interesting is what is happening at the critical point. As we saw before, if you are considering an isothermal process, what is happening? It's happening, for example, if you are considering the van der Waals course, that we have a minimum. Okay? So we have a point of minimum. And if we are plotting what is happening in a graph with pressure and volume, as you know, we have one region where we have the coexistence together, they're existing together, liquid and vapor. Okay? They're together. At the critical point, what is happening is that only one phase exists. So the enthalpy is the same, the specific volume is the same, the internal energy is the same between gas and liquid at this point. Okay? So in this point also, there is an inflection of inflection point. So you see that it's going to have a minimum, but at this point there is only an inflection. So there is second derivative is 0. So at the critical point, what is happening is that the partial derivative of the pressure with respect to the specific volume is equal to 0, but also the second derivative of the pressure with respect to the specific volume is 0. Okay, so this is important to say. Okay, at the critical point, many variables are changing, and are changing even very close to the critical point. Because this is really a kind of singularity in the phase change diagram. It's a kind of singularity point. So, for example, the water becomes compressible, expandable, and so on. This is very, very important because sometimes I saw, even in conferences from colleagues and so on, the incompressible simulations, using VOF, for example, incompressible code, close to the critical point, 0.98, 0.97. I raised my hand. What is happening there? Are you sure? Because what is happening close to the critical point is quite complex. Okay, so you cannot use the usual way, no? It's not possible. Above the critical point, there is no change, variation between liquid and vapor, so it's so-called supercritical points. And so we can use the classical isothermal, the classical hyperbolic behavior for an isothermal process. Also, another point is that we are used to have this kind of temperature and entropy diagram, the so-called Mollier chart, and in this way. We are always plotting in this way. No? We are giving a problem, we are saying this is T, this is S, and this is the region of coexistence between liquid and vapor. But in fact, for example, if you are considering organic fluids, this curve is completely different. And you can think, okay, plus minus is the same. Well, it's not the same because, for example, water is like that. So if you decrease the pressure, you have, let's say, that you are entering in the two-phase system. But for example, for organic fluids, if you're going to decrease the pressure, you're going to have superheated vapor. So the behavior is completely different. So the form of the curve, if you consider one fluid or another, is really very important. Okay? And again, I'm saying that because, again, when you're going to simulate or even doing experiments, you need to consider the fluid that is inside. If you're using propane or using water, you're using an organic mixture, well, you have completely different properties. So you cannot use what you know for water for the other fluids. It seems obvious, of course. Again, I know that most of you knows this, but it's better to remind. Okay, no, I don't have time. So, another point that we need to consider is the so-called metastability, which is very important for multiphase flows. When we are going to have a phase change, okay, in reality, the phase change is not happening instantaneously at the given temperature and pressure. So we are used to think to the Clausius-Clapeyron curve, and we are saying we are going with the 20 degrees, we are going to 2,600 Pascal, and then we are going to have a transition of, for example, for water. Okay? Well, if you are trying to do experiments like that, it doesn't work. You need to be very, very precise to do something like that with system, very accurate system and so on. And in reality, it's not happening something like that. Okay? Why? Because we have always a little bit of metastability. So a condition that is not in equilibrium. So Pt, this expression that is really written on the stone, is valid, but the fluid cannot be there, maybe. At some time, the fluid is going to be in other position close to that condition. Okay? So we are speaking about supercooled vapors, superheated liquids, and supercooled liquids. Okay? Now, if you look at the phase diagram, okay, you have liquid in one position, then you have the coexistence, and then you have the vapor on the other side, which is fine. Okay? So, in fact, inside the region where we have the coexistence of the two phases, we can even use the so-called leverage rule that is saying that if we know the properties of the liquid and the vapor, we can average, we can weight the properties of the liquid and vapor to obtain what is the property of the mixture, liquid and vapor, which is fine. And again, at the critical point, there is no difference anymore. Okay? So there is a transition from the liquid and gas that is very, let's say, very smooth. However, look at this. These are three models of fluids close to, for water, close to the critical point. No? This is, for example, the latent heat of evaporation. The critical point of water is about 373 something, okay, centigrades. Well, the deviation, let's say here, is huge, as you can see. So when you are closer to the critical point, even one of the most simplest property, like the latent heat, is going to deviate a lot between one, let's say, model to another model. And this is happening for all the variables. So you don't know exactly what is happening there. Okay? So you can try, but it's becoming quite complex to work very close to the critical points. And this is for water, and water, we know water very well. If you're considering other fluids, it's worse. So the deviation between different models is really huge. Okay, so pay attention when you're doing experiments or simulations close to the critical condition to have the right properties, or let's say maybe to try a sensitivity analysis to understand what is happening with the different models, because this can be really important. So, according to the thermodynamic inequality, the P over the V is less than 0. This means that the pressure is a decreasing function of volume along an isotherm. Okay, so it's going down. But if you see from this, this plot, well, the slope of the isotherm is not the same. So if you are going to do this calculation of the derivative of the pressure with the volume, you can see that we have, in fact, different sections of this process. Okay, we are going from A to B, no problem. Okay, but then from B to a given point C, we are entering in a so-called metastable condition. So this means that the fluids still exist in a phase where shouldn't exist as a liquid. Should be already something like liquid plus vapor. Okay, but it's still only liquid. So this is the metastable condition. Okay, this inequality is still valid. So we are going down, we are decreasing with the value. And The same is on the opposite side. If we have vapor, and we are going to have a process where we are going to increase the pressure, for example, in isothermal way, we are going from F to E, so we should have vapor and we should start to nucleate liquid, right? Well, we are able to enter, and so again, if you're looking from D to F, the pressure is decreasing with an increase of volume, as the thermodynamic inequality is saying. But we are able to enter inside the zone that is not in equilibrium. In fact, we are going to have vapor where we should have vapor plus liquid. Okay? The point is, can we continue? So can we go from C to D? Where we can stop and so on. In fact, the point is that we cannot go beyond C, and if we are going from F to E to D, we cannot go beyond D. So this means that this region here is not reachable. Okay? Because one way to say is that because in this point, inside the AKB, no way. Okay. AKB region, the thermodynamic inequality is violated. And the thermodynamic inequality is coming from the entropy relation. And the entropy is the entropy. We cannot violate something that is against the sign of the entropy. Okay? For sure. Of course, I didn't demonstrate that because there is no time for that. But we cannot enter. Otherwise, there will be a violation of the second principle. So it doesn't work. So in fact, there is a region where it's possible to go up until C and D. It's possible to go. It's difficult, but it's possible. Beyond that is not possible because otherwise we have a big problem with the entropy. And this is absolutely not possible. So these points are the so-called spinodal curve. So the spinodal curve are this curve here. Curves here. That are defining where we may still have a metastable condition and not. So we can have a metastable condition in this gray zone. We can have a metastable condition in this zone, but not inside the region between the two spinodal curves. Another point no, I don't have time for that. Another point that we can also consider what is happening in terms of this equation and so on. So I don't have time to enter in all these details. Are very interesting. I give you the PDF, but I cannot enter. It's too much. Sorry for that. Because it's a very long demonstration, so I am not able to go. So, what is happening then? For example, this is P rho, is the pressure density for the methane isotherm. Since it's a density, I put this graph because instead of the classical specific volume, here we have the density, and you can see that is inverted. So we have, on the left, we have the gas, and on the right, we have the liquid. But also in this case, we can distinguish between a region of the pure gas, metastable gas, a region that is unreachable, we cannot do anything, metastable liquid, and liquid. Okay? And we can have also curves like that, also interesting. So we have temperature here and pressure, and we can have for the different pressure we can have the spinodal curve. The the saturation line, and then in between we have the metastable conditions. The metastable conditions are very important because they are linked to the nucleation. What is the nucleation? This will be a course. We can speak about nucleation for, let's say, 20 hours, okay? By the way, I just wrote a review about nucleation for International Journal of Multiphase Flows, and I think that will be out with other authors, of course. I was not alone, okay? And so I think that it's going out maybe this week, I hope. So if it's going out this week, I can give you the reference. And I spoke about the classical nucleation theory. I wrote about that because the classical nucleation theory is a classical theory for nucleation, and in many cases it doesn't work. It's too classical. What is interesting, though, is that what is happening just close to the saturation line when we are going in the metastable condition is the nucleation. So we have the appearance of the other phase. So imagine to have liquid. We are going in the direction of the vapor. So we are going to, with let's say, we are heating up. And at the given point, we have the condition that we are entering a little bit in the metastable condition. So the probability to have the nucleation are higher and higher and higher. Are becoming infinite, so 1, let's say probability 1, in this case 1, when we are going to the spinodal. So this means that it's not possible to overcome, because we are going to nucleate and we are going to have the other phase. Okay? But at the very beginning, what is happening is that the classical nucleation theory can give us an idea of when we have the nucleation. Okay? Imagine water. We know that the water is going to boil at 100 degrees. Let's say in a very ideal condition, but let's say it like that. Okay? So at 1 atmosphere, we're at 100 degrees. This was measured, so it's possible. Okay? Good. Then we are going there. At 100.05, we are having a given probability to have some nucleation. If we are increasing temperature, then of course we are going to have nucleation. So it's possible to describe what is happening inside this region where we have more and more chances to have nucleation, so to produce, for example, the vapor from the liquid. Okay? And this is a very nice work from in fluid phase equilibrium about that. Okay, so what is interesting is that if you're looking at the van der Waals equation, okay, the van der Waals law, we can have this kind of curve, let's say, no? And you can see here, it's very interesting. We can prove that this area is equal to this one. This area is equal to this one here, and so on and so on. It's very interesting. But what is interesting also to know is that we have this behavior for the isotherm pressure. And see, look at this situation. Here the pressure is 0, and we have stretched liquid. So this means that here we have something. So again, something that everybody is saying in the undergraduate courses is that the pressure is only positive, which is wrong. The pressure can be negative. Okay, and again, I don't have time to enter in this field, which is quite interesting. But what is happening is that, in fact, the pressure can be negative because we are stretching the water. And how can you think about that? How is it possible to think that we can stretch? We have, instead of having positive pressure, we have negative pressures. Okay? Well, there are different ways to do it. There are different experiments even. And one experiment is the centrifugal method. So if you put, let's say, a liquid inside a kind of centrifuge like this one, and you're doing the experiment very accurately, inside, in the middle, the liquid should go in one direction and the other. So in fact, you are stretching the liquid in the two directions. And you are reaching a negative pressure. And there are other experiments that are quite interesting. And for example, especially from this guy, is a French guy, Copen. And I think that Copen was able to go with the water at minus 20 megapascal. Minus, not joking, minus 20 megapascal, which is a lot, okay? Which is a lot. And one can say, why are you saying that? For example, now I'm studying a lot of negative pressure. I'm doing a lot of work on negative pressure. Why? Because when you're dealing, for example, with the flash atomization, okay, very rapid processes, you may land in metastable condition in these conditions, because you are going from the liquid to the vapor so fast at low temperature that you are entering in the negative pressure regime. You are stretching the liquid with the flash atomization, for example, of hydrogen and so on. So it can be very interesting, because if you are not considering that, you are, let's say, not considering really the real physics that is happening there. Please.
What exactly is negative pressure
Imagine negative pressure. It means usually you're thinking the pressure is something that is normal to a system, and the vector is toward the inside. So if you're considering normal as usual, like in analysis, it's always negative in terms of the normal direction, because it's going to the hydrostatic pressure. It's going to press inside. Now think about a bulk of liquid with the molecules that are going inside. Okay, the pressure means that you have again the pressure that is going to be linked to the fact that someone is pressing. So in terms of the negative pressure, it's something like inside the molecules tend to go outside, to expand. They are still together. So you have still a liquid, but it's going to be stretched. So this means that in this case, since you have a force that is going from inside to outside, you are going with the normal, so you have a negative pressure. You can.
Kind of low pressures is it applicable for space applications? Very low pressures like this.
Well, it's applicable every time that you have a process. I don't know which kind of process in space you're thinking. It's not a question of low pressure. No, just a moment. Maybe I understood the question. There is no, I mean, we are thinking in vacuum, for example. This is a low pressure condition. But it's nothing to do with this. This is done with when you have a phase change. Okay? Or we have conditions like these ones, where you have, let's say, a condition where you have a stretch of the fluid. But you need to have the fluid. You need to have matter. When you have a low pressure, you're considering a vacuum. So you have only molecules inside. So you are considering ultra vacuum, for example. You don't have matter. You don't have mass. Here we are thinking to something that has a mass. Something that has billions of molecules inside. But still is giving us, if you are measuring, you are giving us the pressure in the other way. So it's a negative pressure. You are stretching the fluid. And this is happening. So this is, of course, a metastable condition, because it's happening here, say that is outside, but it's happening here, outside the equilibrium domain. But it's interesting because nobody is thinking to that. So it seems that, okay, P must be bigger than 0. Well, no. If you're doing a phase change, not a low vacuum. So it's not possible to think, I'm going to 1 bar, 0.5, 0, then we are going to the other side. No, it doesn't work like that. You need to have matter, and you need to process, you have a phase change, isothermal. It's an isothermal phase change when you're going to have the metastability, and in this case you can enter in the zone of negative pressure. And this is also working with the cavitation. there is a different experiments with that during the cavitation you may have negative pressure. I'm sorry for you, but it's like that. Cavitation is quite complex. It's very complex. Yeah. It's a kind of stretch also in this case. Then, now the time is finished, but think about the fact that we may have all what I said today also for multi-component systems. So for systems where we have different chemical species, the things are becoming even more complicated. Look at the time. My time is almost over, but let's say this is another point, something also to say. I don't have time. I will say something important for the heat pipe, maybe, because someone of you is working with heat pipes. A classical multi-component problem when you have a heat pipe is the fact that inside the fluid you have dissolved gas. So you have the liquid, or you are using, for example, ammonia, you're using water, you're using propane, whatever, acetone. But some gas, air gas, is inside. You did the vacuum, you try to do whatever, but some gas is there, okay? How can you check how much gas is inside? Well, you need to consider the fact that when you have a second component inside, the saturation pressure doesn't correspond anymore to the saturation temperature for the pure fluid. So this means that if you are considering, for example, a given temperature, you should expect a given pressure. But if you have dissolved gas inside, you're going to find a different pressure, a lower pressure. So this means that you have something there, okay, for example. Okay? So there is something that is a second component that is still present in the liquid. And you may use, for example, the Raoult law to estimate how much is the specific quantity of the other component inside what you believe is a pure liquid. Okay? I don't have time for that, but it's interesting. Okay, no, stop here because otherwise it's... As I said, this was only a kind of a very short resume about the physics. I think that everybody in this room knows about that. Maybe not the negative pressure. For someone was a surprise. I don't know, maybe not, but okay. Because we wanted to have a bridging lesson today, okay? Tomorrow we are starting with I think some matter related to multiphase flows and so on. We are going deeper, let's say. But I think that with Arvin, we believe that was important to give, let's say, one day of a kind of resume of 2 or 3 courses, undergraduate courses in thermodynamics, heat transfer, and fluid mechanics. But I think that is important to give. I will stay until 1 p.m. Okay, so I have 1 hour. I stay here. If you have questions about your work, PhD, something that you want to ask, I'm here. Okay? Is it fine? Okay. Thank you so much.